and welcome back to our lecture series on statistics. Today, we're going to be introducing the topics of probability and proportions, figuring out how that applies in statistics, and then we're going to combine those ideas with the Z distribution that we talked about in the last lecture, and we're going to use those ideas together to figure out how to establish whether or not a treatment effect exists in our research. So getting into some more application sides of statistics today. These are the symbols that we're going to be using today, pretty much the same as last time. And the concepts, as I said before, proportions, we're going to talk a little bit about percentile ranks, and then we're also going to bring back the idea of mathematical distributions and z-scores. So first and foremost, what is probability from a statistics perspective? From a statistics perspective, probability is used to predict the type of samples that we are likely to obtain from a population. So it establishes a connection between samples and populations in the forward direction. We've talked previously about how in research, we often do our research on the sample and then use inferential statistics to draw conclusions about our population after the fact. But probability is important to take a sample or take a population and figure out what type of sample you should use in order to make a statistically representative sample. So probability is the connection in the opposite direction of inferential statistics. So probability is defined for any specific outcome as a fraction or proportion of all the possible outcomes. So if you have the possible outcomes A, B, C, and D, let's just say, the probability that you would get A out of all of those would be found using this formula. You would take the number of A outcomes that you got and then divide it by the total number of possible outcomes. So for example, if we asked, what is the probability of pulling a king from a deck of cards? The other question that we're basically asking is, what proportion of the whole deck consists of kings? We would say there are 4 possible outcomes, 4 possible king cards, and there are 52 total possible outcomes because there are 52 cards in a deck. So you would say 4 out of 52 is equal to 1 over 13, which is about an 8% probability of drawing a king from a deck of cards. When we are talking about probability in statistics, we keep it with a limited range between 0 and 1. So a probability of 0 means that the event never occurs, whereas a probability of 1 means that the event always occurs, both of which are rare. So in scientific research, we use something called random sampling to assure that we have a representative and unbiased sample. In other words, random sampling is kind of a precursor to even using probability in statistics. And there are a couple of things that need to be true about the way that we got our sample in order for us to have accurate probability. The first is that each individual in our population needs to have an equal chance of being selected. So that means that there's going to be no bias in our selection process. And this is called a simple random sample. An example of this is, let's say you have a bag of multicolored marbles or blocks. Excuse me. A simple random sample of those would be if you just closed your eyes, reached into the bag, and pulled one out. You had the exact same chance of selecting every single individual marble or individual block in that set. That's called a simple random sample. The second requirement states that if more than one individual is being selected, then the probabilities need to stay constant from one selection to the next. So in order to make this happen, we use something called random sampling with replacement. So if we go back to our marbles or our blocks bag, in order to ensure that the probability stays constant, as we take out one marble, we would need to add another marble in before we make our next selection, so that the total number of marbles stays the same from one selection to the next. So I have the exact same chance of drawing out, the probabilities are exactly the same for the second marble I drew out as was for the first marble that I drew out. A sample, when we meet both of those requirements, the sample that we get is called an independent random sample, or in summary, I guess, that the probability of selecting any particular individual from our population is independent of the individuals that have already been selected for the sample. We generally, because an independent random sample is required for a lot of the statistical applications that we're going to be running, we generally just assume that this is the way that samples were selected. And we'll even just drop the independent. We'll just usually call it random sampling. But remember, when you hear the word random sampling, it means that both of these requirements need to have been fulfilled. So, the situations in science in which we are concerned with probability usually involve a population of scores, and we can represent those scores in something called a frequency distribution. As it says here, frequency distribution graphs can be used to represent the entire population, where different portions of our graph are going to represent different portions of the population. And because in this situation, proportions and probabilities are equivalent, any particular portion of the graph corresponds to a particular probability. So for example, this frequency distribution histogram has a population number of 10 scores. This represents 10 scores. If I were to ask you, let's say we're taking a random sample of n equals 1, we're just drawing one of these. What is the probability that we are going to get an individual who had a score higher than 4? To use this frequency distribution histogram, you would just highlight the part of the figure that corresponds to the portion of the whole population who had scores greater than 4, which is this shaded part here. And we would say, okay, that is 2 out of the total 10, which is going to equal 1/5, which is roughly 20, which is not roughly, it is 20%. So the probability of obtaining an individual with a score that is more than 4 in this population is going to be 20%. And that's how we use these kinds of frequency distribution histograms. So we've discussed this before, but I want a quick recap of what a normal distribution is. It's the most commonly used theoretical distribution. It's symmetrical, that bell-shaped curve, highest frequencies in the middle, and it tapers off to the sides, remember? The mean, the median, and the mode are all in the same exact place. All normal distributions are going to have the same shape, but they can have different means and different standard deviations. And the most useful way, this last bullet here is important, the most useful way to define relative location in a normal distribution is to state what proportion of the area is above or below a given score, usually the mean, but we can also use z-scores. So the standard normal distribution set up here is any normal distribution that's been transformed into a z-score distribution. So basically what we were learning how to do in the last lecture, transform any raw scores into z-scores. Once we've transformed it into a z-score distribution, it's also called the standard normal distribution. And an important application of this is, since all z-score distributions are going to have the same mean and the same standard deviations, if the population is normal, your z-score distribution will also be normal, and you can compute the probabilities of obtaining particular z-scores, which is really, really awesome. And because all normal distributions have the same shape, a particular z-score is going to fall in the same location on any normal distribution. So we can use it as a standard. Let's look at what that looks like in a graph. So when the area under the normal curve is being used to determine proportions of the population, we're going to define the whole area as 1 or 100%. So this is all going to be 100%. And because the locations in this distribution are identified by z-scores, the percentages shown in this figure are going to apply to any normal distribution, regardless of the values for mean and standard deviation. So what this means is, for example, if your score on a test translated to a z-score of 1, so if you were right here, or if you were one standard deviation above any mean on any normal distribution, that means that you scored better than 83.95% of the population. All of the rest of these percentages added up. And that's going to be consistent on any normal distribution, whether or not it's been converted to a z-score, which is really, really cool. We'll come back to this image later on, but I want to discuss one more topic before we move on. I want to introduce something called the binomial distribution. When a variable is measured on a scale that has exactly two categories, the resulting data are called binomial. So this can be a naturally occurring binomial, such as you have a study that's studying sex or gender. So your binomial is male versus female. Or you can have an artificial binomial where you're like a pass-fail, right? For any way that you get the binomial, the probability associated with each of the categories has to be 0.5 or 1/2. A good example of a binomial in an application is a coin toss. The probability of getting heads or tails is the same, and it's 1/2 for both of them. Two possible outcomes. Binomial distributions are then formed once you've performed a binomial test many, many times and have observed it. For example, 100 coin tosses. After those 100 coin tosses, if you charted your results, that would be called a binomial distribution. The important things to remember in terms of the variables that we're going to be talking about, the two outcomes are usually identified as A and B. So like the probability of getting heads would be A and tails would be B. N is going to be the number of individuals or observations in your sample, so like the number of coin tosses. And then X is going to be the number of times category A occurs, for example. Okay, let's move on here. A lot of times the probability of A is also identified as P, and the probability of B, or the second outcome, is identified as Q. So the probability of A and the probability of B together have to equal 1. Let's look at how we would create a binomial distribution here. So an experiment with a binomial distribution has to have these following properties. There's going to be n repeated trials. Each trial can result in either an A outcome or a B outcome. The probability of A, and by extension, the probability of B, is the same on every trial, 1/2 every time, and then the trials are independent from each other. Let's do one of these. So let's say we're doing a coin toss experiment. Our n value is going to be 2. We're only going to toss the coin twice. The possible outcomes are either heads or tails, and the probability of heads or tails is 0.5 on every trial, and the trials are independent. Let's look at all of the possible outcomes we could get from a 2-coin toss experiment. The first is that we got 2 tails, 0 heads. The second is we got tails and then heads. The third possibility is heads and tails. And the last possibility is 2 heads. I also want to acknowledge that this is an American quarter. So this is the currency in the United States. So your currency, depending on where you're watching this, may or may not be the same. But yeah, that's what we used here. So, oops, we'll get to that in a second. Here are the probabilities of getting all of these outcomes. The probability of getting 0 heads is going to be 1/4. The probability of getting 1 head is 0.5 or 1/2. And the probability of getting 2 heads is 1/4 or 0.25. If we graph that out on a frequency distribution histogram, this is what our probability looks like. Interesting shape, right? Keep that in mind. Let's say that we increase our n to 4, and then we try. These are all of the possible outcomes from a 4-coin toss. If we graph these possible outcomes and their associated probabilities on a probability histogram, it looks like this. Interesting shape again. And now let's do the same thing, but with 6. And we're getting a pretty consistent shape here, right? No matter how many we use. When we use a binomial distribution, I'm actually going to go to this one first. When we use a binomial distribution, the higher our n value gets, the closer it gets to looking like a normal distribution. The differences are that a binomial distribution is going to be discrete. There's going to be steps like this. And then the normal distribution is continuous. It's going to be smooth. So the normal distribution is only an approximation of a true binomial distribution, but the area under the distribution is pretty much equivalent. And that's what we care about when we're calculating probability. So going back to this one really quickly. When Pn and Qn, those two values we talked about at the beginning, are both equal to or greater than 10, then the binomial distribution will closely approximate a normal distribution. That's like the limit, basically. It has to be 10 or more. The mean is going to be Pn, and our standard deviation is going to be the square root of NPQ. I'm not going to go in how we figured those out, but they're important to know because here, oops, sorry, give me one sec. Because using that information here of the mean and the standard deviation, we can slightly change our z-score formula from a couple lectures ago to represent how to transform a binomial distribution into a z-score distribution. This is the way to do it. Instead of mean, you're going to use Pn, and instead of standard deviation, you're going to use this value. So right here, the fact that the binomial distribution tends to be normal in shape means that we can compute probability values directly from z-scores using something called the unit normal table. We're going to talk about that later on in our lectures, what the unit normal table is. But for your information, it's just a table that we use to establish the connection between z-scores and clinical or statistically significant results. Okay, here is an example of how we would apply this idea in research using inferential statistics. We're hopping ahead a little bit, but we are going to use probability to determine if evidence for a treatment effect is likely to exist. And the way that we do that is we say, under the normal distribution, about 95% of our results for any sample, any population, are going to be within these two markers. The z-score can change. It's not always negative 1.96, but usually it is. And that's what we use the unit normal table for, to figure out what these z values specifically are. But 95% of our values are called the high probability values that are going to be close to the mean, within about some standard deviations of it. However, if after we have basically performed a treatment in an experiment that we're running, if our resulting scores fall in this outside or extreme 5% after we transform it into a z-score, that means that those scores are very unlikely to be obtained from the original population. And so if our score falls either in these lower or upper 5%, then that means that we have some evidence that there was a treatment effect, that something changed and the treatment had an effect. Okay, we're going to take a break here, and then we're going to come back and finish the rest of this lecture on probability in a minute. So I'll see you in the next recording.